Hi students, Mr. Danaher here. Today we're going to be talking about molecule polarity. We've talked about how different types of bonded substances have different types of properties. So metallically bonded substances have certain properties, whereas ionic and covalent substances have different properties. And specifically, polar and nonpolar covalent substances have different properties from each other. So it's really important that we can determine if a molecule is polar or nonpolar. In order to determine if a molecule is polar or not, there are two main things we need to look at. The first thing is we need to look at the polarity of the bonds in that molecule. The second thing is we need to look at the shape of that molecule to determine if it's polar or not. And so those two factors are going to play into determining whether a molecule is polar or nonpolar as a unit. Let's talk about bond polarity first. Remember that in a polar bond, that means that the electrons are shared unequally. So if we have two elements, and we'll just take like oxygen and hydrogen here, and we look at the pair of electrons, so I'll draw those as like a pair here. Those are being shared between those two atoms, right? Now we can look at the polarity the electronegativity of each bond, and I've placed some electronegativity values here on this table. And we see that oxygen has an electronegativity of 3.5, and hydrogen over here has an electronegativity of 2.1. So if we look at just that particular bond between those two, what's happening with those electrons? Well, the electronegativity of oxygen is quite a bit higher than that of hydrogen. That means the electrons are going to be getting pulled more towards the oxygen side. That's going to create what we call a dipole, meaning a dipole moment is just an arrow showing us that the electrons are being pulled to one side of that bond. In this case, it's being pulled towards the oxygen because oxygen is the more electronegative element in that bond. Keep in mind, if we had two elements that have the same electronegativity, like two oxygen molecules, okay, when they both have a pull or electronegativity of 3.5, there's not going to be a bond dipole because the electrons are being shared equally, since both of those oxygens pull equally on the shared electrons. So this is going to be a nonpolar bond. This is going to be polar because the electrons are being shifted towards one side of the molecule. Because they're being shifted towards the oxygen side and electrons are negative, that's going to give us a partial negative charge over on this oxygen side and a partial positive charge over here. So if we have only one bond in a molecule, it's easy to tell if that molecule is polar or not. If it has a polar bond, then the molecule is going to be polar. If the bond between the atoms is nonpolar, then it's going to be a nonpolar molecule. But most of the molecules that exist around us, the thousands and thousands of different covalent molecules, have more than one bond. And so there's more that we need to look at than just one bond. So we'll kind of take a look at what if we have more than one bond in a molecule. And that's when the shape comes into play. We really need to look at the shape of a molecule. Now, in order to determine the shape, it's really important that we can draw the Lewis structure. And the Lewis structure is going to be used to determine the shape. And then the shape is going to play into the polarity along with the bond dipoles, as we just discussed. So let's look at a molecule, for example, carbon dioxide, okay, CO2, right? We want to first draw the Lewis structure to determine if this is a polar molecule. To draw the Lewis structure, we need to determine the number of valence electrons, and carbon has 4, and each oxygen has 6, so that's a total of 12, all right? So our total number of valence electrons that we need to show is 16. We can draw carbon as our central atom and then bond each oxygen to that carbon, okay? And then we need to place the rest of all 16 of our valence electrons. So we have 2 in this bond and 2 more in that bond. That's 4, 6, 8, 10, 12, 14, 16. So the total number of valence electrons is 16, and I've placed all of those. We can see that carbon is not full. It only has 2 4 electrons. And so that means that we need to make a double bond with these other oxygens here. So when we look at the Lewis structure of this molecule, and now say, well, there's only 2 bonding domains, and on the central carbon there are no other electrons. Those 2 bonding domains, those double bonds, are going to get as far away from each other as possible, which is going to be 120 degrees. And so when we draw this now, this is the second step after we've drawn the correct Lewis structure, we redraw the molecule in the correct shape. And notice I'm not adding the extra electrons on the oxygens because they're not really necessary now that we know the shape. The extra electrons are really just to get us to the correct Lewis structure so that we can then determine the shape. So if we look at the shape of this molecule now, this is a linear molecule. Now we want to, now that we've got the correct shape, we can go ahead and draw in the bond dipoles. So we want to go and look at the electronegativities of each element. You can see that carbon on the periodic table has an electronegativity of 2.5, and each oxygen has an electronegativity of 3.5. Okay, so we know that there are going to be bond dipoles. If we look at one of those double bonds between carbon and oxygen, we can see that oxygen is pulling with a difference of 1. 2.5 to 3.5 is a difference of 1. That's a relatively high difference in electronegativity. So when we draw the bond dipole arrows, the dipole arrows are sort of like a vector. And so the bigger the difference, the bigger the pull, the bigger the arrow we're going to draw. So I'm going to draw a relatively large bond dipole arrow showing that pull. Now I'm also going to draw one on this bond, and the difference is the same. So I'll draw the same size arrow, but pointing the direction that the electrons are getting pulled. Now if we look at those two arrows, we want to consider this molecule as a whole unit. And I like to just think of it as a sphere or some shape that's that we can see the sides of. And so if we just draw a circle around the whole molecule, now we look at where are the electrons getting pulled. Well, this dipole is pulling the electrons this direction. And the other dipole, the other oxygen, is pulling the electrons this direction. But because this is a linear molecule, those two dipoles, they cancel each other out. And one way we can look at this is we can actually draw these vector arrows in tip to tail. So if we take just one arrow, like the first one here, and I draw it like this, the same size and same direction, and then I take the second arrow, and I start at the tip of this arrow, and I draw that arrow, the other arrow, just the same way, where do we end up? Well, we end up right back where we started. That's telling us that these vectors, or these bond dipoles, they cancel each other out. This would be a nonpolar molecule, okay? That's because even though there are bond dipoles, the bond dipoles, because of the shape, the linear shape of this carbon dioxide molecule, they're going to cancel each other out. That means this is a nonpolar molecule. So again, we have to look at the shape of the molecule and the bond dipoles, if they exist, to determine if a molecule is polar or not. Let's go ahead and look at another molecule and determine if it's polar. So this time we're going to look at hydrogen cyanide, HCN. Now I'm not going to go through the process of drawing the Lewis structures for these. I'm just going to show you what they would look like. If we drew the Lewis structure for this, it would look like this, right? And now when we consider the shape of it, again, we have two bonding domains. We have 1, 2, and there are no extra pairs of electrons on that central carbon. That means this is going to be a linear molecule, again, just like carbon dioxide was. So I'm going to redraw this to the correct shape and show that linear molecule. Okay, so step 1, we drew the Lewis structure. Step 2, we drew the correct shape of the molecule so that now we can draw in the bond dipoles if they exist. So let's go ahead and look at our electronegativity values. The electronegativity of hydrogen is 2.1, carbon is 2.5, and nitrogen is 3.0. We're going to go ahead and draw in our bond dipoles now. So remember, they're always going to point towards the more electronegative element for every bond. And keep in mind that the bigger the difference, the bigger the arrow we're going to draw, showing a greater pull in that direction. So in the carbon-nitrogen bond here, I have a difference of 0.5, which is relatively low, and actually some chemists would say that's a nonpolar bond, but it is slightly polar. So we're going to draw a dipole arrow, small dipole arrow pointing towards the nitrogen. If we consider the hydrogen-carbon bond here, there's a difference of 0.4, which again is fairly low, but it does shift the electrons slightly towards the carbon. So I'll draw a small arrow that direction. So we can see, again, if we draw a circle around this linear molecule, and consider where are the electrons getting pulled towards. In general, they're getting pulled towards the nitrogen side of this molecule. And we can do the same vector addition. We can take this first arrow and draw it like this, okay? And then add the second arrow to it. So we just add the tip of the second arrow here, or the tail, and we move this way. And we can see overall there is a molecule dipole, okay, pointing this direction, pointing towards the nitrogen. And I neglected to do this with the last molecule, carbon dioxide. Well, I didn't neglect to do it. It's nonpolar, so we wouldn't have a molecule dipole or partial charges. But in this case, we do have a molecule dipole because the bond dipoles don't cancel each other out. So if I were to draw a molecule dipole that shows the direction of the electrons getting pulled in the whole molecule, I would draw something like this, an arrow pointing from the hydrogen side over here towards the nitrogen side over here. Now that also means because those electrons are getting shifted towards this side of the entire molecule and electrons are negatively charged, this side of the molecule is going to have a partial negative charge since electrons are negatively charged. And so they're getting pulled away from this side of the molecule. The opposite pole is going to be our positive charge. And again, that's why they're called polar molecules, right? Because we have two sides, a partially negative side and a partially positive side. This is a polar molecule because there are bond dipoles, and the bond dipoles do not cancel each other out. Those were two linear molecules. So one thing you'll notice is sometimes linear molecules are going to be polar and sometimes they're not. So if we ever have a linear molecule, we definitely need to draw in the bond dipoles to see if it's polar or not. Let's look at an example of a bent molecule, and we'll use a very common one. It's water, of course, here, H2O. And when we draw the Lewis structure for H2O, we get something like this, right? Right. So no matter how you drew that, now some people will draw it like this, the Lewis structure, okay, and that's fine. Either way you draw it, you'll notice that there's two bonding domains, but we also have two lone pairs of electrons on the water molecule. That's going to end up bending this molecule into a bent shape. And so I'm going to redraw that, like I've said, we're going to redraw it to the correct shape here in some kind of a bent fashion. Okay, now we have a better representation of where those bonds are relative to each other. If we were to keep it like this, which would make it seem like it's linear, when we draw in bond dipoles, they might seem to cancel out, and that's not going to be a good representation whenever we're trying to determine if the molecule is polar or not. So it's always important that you redraw the molecule into its correct shape. In a bent molecule, we want to show that shape here. So let's go ahead and draw in so again, step 1, draw your molecular Lewis structure. Step 2, determine the shape and redraw it. Now we want to see if there are any bond dipoles. In this case, again, we do have bond dipoles because hydrogens have an electronegativity of 2.1 and oxygen is 3.5. So we have a relatively large difference in electronegativity. And again, I'm going to draw my vectors, my bond dipoles, pointing towards the more electronegative oxygen. It's got a higher pole, and I'm going to do that for both of these. Okay, I'm drawing them a little bigger because that pole is a little bit bigger since there's a bigger difference between the oxygen and hydrogen electronegativities. So again, if we draw just a circle around our molecule here, and then we add up those vectors. Let me show you what that looks like. So I'm going to take this arrow first, and I'm going to draw it just like it is, okay? And then I'm going to take the second arrow, and I'm going to start the tail of the second arrow there, and I'm going to draw it just the way it is, like this. And when we do that, we can see that the electrons are getting pulled this direction. So the molecule dipole for this water molecule is going to be like this. It's going to be pointing towards the oxygen and away from the hydrogens. That's showing that the electrons are getting shifted toward the oxygen side. And again, electrons have a negative charge, so we get a partially negative charge on the oxygen side. The electrons are getting pulled away from this side of the molecule, so the opposite side of that has a partial positive charge. This is a polar molecule because we have the shifted electrons towards the oxygen, giving us a partially negative pole and a partially positive pole. So we can see here a bent molecule Typically, if a bent molecule has dipoles, if the bonds have dipoles, it's going to be a polar molecule. If we had a substance like, let's see here. If we had a substance like ozone, O3, that's actually going to look like this. And I'm not going to draw the whole Lewis structure out. It is going to be a bent molecule. But you'll notice that because the electronegativities on the oxygens are all the same, we would assume that this is not going to be a polar molecule because there are no bond dipoles to create polarity in this molecule. And for our purposes in our class, we'll say that's okay. We're going to say this is a nonpolar molecule. However, I just want you to know that there are other factors in play here, like formal charges, that do give ozone a bit of a polar characteristics to it. So as always in general chemistry, we're going to give you general ideas, and we're going to skip over some more complex topics, and hopefully you'll learn about those in higher level classes if you choose to take those. So most of the time, bent molecules are polar, but if they don't have bond dipoles, then they're not going to be polar. And that's true of most molecules. If a molecule has no bond dipoles, we can assume that it's going to be a nonpolar molecule. Let's go ahead and move on to some other shapes. So I'm going to show you the structure of an exception to the octet rule, which is BF3, boron trifluoride. And so if we draw the Lewis structure, if I asked you to draw the Lewis structure for this, you might get confused because it doesn't quite work out like we're used to. This is an exception to the octet rule because boron is perfectly happy just having 6 valence electrons instead of having 8. And there are some exceptions like that, and that's okay. In our class, we won't expect you to know all those exceptions, but I do want you to just know that there are some exceptions out there. So if we look at this, we have a central atom, and I didn't add all the extra electrons on here, so I'll do that really quick just to draw the right Lewis structure. That looks better. And when we look at the shape of this, we can see there are 3 bonding domains and no extra electrons on that boron, the central atom. So when we draw it to the correct shape, how are those bonds going to spread out at what angle in order to get as far away from each other as possible? And the answer is they're going to spread out at about 120 degrees from each other. So I'm trying to draw that somewhat accurately. These bonds are all about 120 degrees from each other. You'll notice this is called a trigonal planar. Okay, I'll just abbreviate that. A trigonal planar molecule. Now, in a trigonal planar molecule, we do have the possibility of being polar or nonpolar. So we do have to put in the bond dipoles and see if the molecule is going to be polar or not. So the fluorine has a pole of 4.0 electronegativity for all of those, and the borons are 2.0. That's a really big difference, too. In fact, it's getting really close to being an ionic bond, and some chemists, again, would say that that's more ionic than it is polar covalent. But that's a continuum. And so we'll draw in our vectors, arrows, showing the direction here. And again, I'm going to make those pretty big because 2.0 is a big difference. And we'll just do this. Okay. So try to draw those all the same size. And now we can do our vector addition and see what we get. I'll take this first arrow here and draw it just starting at this point. Okay, and then I'll take my second arrow here, and I'll draw that going this direction, roughly getting it right there, and then this last arrow going this direction. And if I was a better, more accurate representation, we would see that the arrows start exactly where they ended. So basically what we can see there is all of those bond dipoles are going to cancel each other out. What does that mean about this molecule? We have very polar bonds, but since the bond dipoles pull in equal and opposite directions and they cancel each other out, this is going to be a nonpolar molecule. Okay? That means we're not going to have any molecular dipole, and there are going to be no partial charges. So basically the electrons are distributed equally throughout this molecule, making it nonpolar. Let's look at another trigonal planar molecule that is polar. Okay. And we will look at formaldehyde here, CH2O. So when we draw that, again, I'm not going to go through all the steps of the Lewis structure, but when we draw it out, it looks like this. Okay, and I'll put the extra electrons on there. So the Lewis structure looks like this. When we look at this molecule, it's really important that we redraw it to the correct shape because it's going to be trigonal planar. We have 3 bonding domains, 1, 2, 3. No extra electrons on the central carbon to bend those into a pyramidal shape. So this is going to be a trigonal planar molecule. So we'll redraw it to the correct shape with 120-degree bond angles, or as close to that as I can get with my freehand drawing here. Okay. Now again, trigonal planar can be polar or nonpolar depending on how the bond dipoles interact with each other. So our hydrogen is a 2.1, our carbon is a 2.5, and our oxygen is a 3.5. So now let's draw in our bond dipoles. First I'll look at the carbon-oxygen bond, and the difference there is 2.5 to 3.5 is 1, so that's a relatively large difference. Draw a bigger arrow. Now 2.1 to 2.5 is only 0.4 difference. It's a small difference, but it is going to point towards the carbon. I'm going to draw a small arrow there. I'm going to draw a small arrow here, showing that there's a small difference there pulling towards the carbon. Overall, again, if we look at this molecule as a whole unit, and we see, are the electrons getting shifted towards one side, or does it seem like the dipoles cancel each other out? Well, they're getting shifted towards the oxygen side. And I can show that if I draw my vectors here. So I'll start here. I'll draw my carbon-oxygen arrow, relatively the same size. Then I'll take this hydrogen-carbon one and try to draw a small one there. And then I'll draw this other hydrogen-carbon arrow, which is kind of going in this direction here. Okay, so if I see where I started here to where I ended here and connect that, that's going to be my molecule dipole. It's pointing from the hydrogens towards the oxygen. Again, because the electrons are getting pulled towards this side of the molecule and electrons are negative, we're going to have a partial negative charge and a partial positive charge here. Okay. This is a polar molecule because our bond dipoles do not cancel each other out, and we have an overall shifting of the electrons towards one side of the molecule. Okay, let's look at a couple more molecules here. So the next one we'll look at is a pyramidal molecule, NH3. So we draw the Lewis structure for NH3, and we're going to get something like this. This is ammonia, by the way, common household product. Okay, and when we look at the shape of this, we can see that this is, because there are 3 bonding domains, but there's also this lone pair right here. This lone pair is going to push on all of these bonding pairs, and we're going to get that pyramidal shape. So when I draw a pyramidal molecule, I usually kind of push those bonding domains all towards the bottom, kind of clump them together a little bit, showing that they're getting repelled by this lone pair that's up here. Right, and then that helps me see the bond dipole direction a little bit more. And if you look at a 3D representation of a pyramidal molecule, that'll make a little bit more sense. Let's go ahead and draw in our bond dipoles. Again, hydrogen is 2.1 and nitrogen is 3.0. So we have a difference of about 0.9 for all of these bonds, and all the bond dipoles are going to be pointing towards the nitrogen. And I should draw them about the same size, but again, my artistic skills are minimal here. And we can see, even just by looking at that, we don't even need to try to draw in the vector addition thing. We can just look at this and see all the electrons are getting pulled towards the nitrogen side here, right? And so we know this is going to be the partially negative side. And the hydrogen, the lower part of this, and again, when I say lower, I just typically draw it that way. There is no lower, higher, up, down, left, right when it comes to molecules. Their orientation is irrelevant of their polarity. This is going to be our partial positive side. So we have a molecule dipole that's pointing towards the nitrogen and away from the hydrogens. So this is a polar molecule. Like bent molecules, pyramidal molecules are almost always going to be polar as well, because if there are bond dipoles, there's really no way for those dipoles to cancel each other out because of their shape. So bent molecules and pyramidal molecules, if they have bond dipoles, they are going to be polar. The last shape that I want to look at is tetrahedral. So let's look at two different tetrahedral molecules. First, we'll look at CF4, carbon tetrafluoride. Okay, and when we draw the Lewis structure for that, it's going to look like this. Here. Now, I'm not going to draw in all the extra electrons on the fluorines because I don't want to waste your time on that. But we're going to see this is a tetrahedral molecule. Now, for the purposes of shape, in 3 dimensions, tetrahedral doesn't look like this. But in terms of determining polarity, it works fine to draw it like this. So just for the purpose of the procedure here, I'll go ahead and redraw it. But this is the same thing as I drew above. All right. When we draw it like this, now we have a good representation of the directions of the bonds compared to each other. And like I said, this will be good enough to show us where the direction of the electrons are going. Carbon is 2.5, fluorine is 4.0. So we're going to have fairly large bond dipoles, all pointing towards the fluorines because fluorine's the most electronegative element. Ooh, that was a bad one. Okay. And we can already tell that all of these bond dipoles are going to cancel each other out. We could do the vector addition thing, and if we do that, we're going to get this, plus this, plus this, plus this. And you're going to see we get back right where we started. This is going to be a nonpolar molecule because all of those bonds, the dipoles, are in equal and opposite directions, and so they're going to cancel each other out. So this is going to be a nonpolar molecule. No bond dipoles, there are bond dipoles, no molecule dipole, and no partial charges, since this is nonpolar. Let's look at another tetrahedral molecule and see an example of one that is polar. So we'll use carbon, CH2F2. So when we draw the Lewis structure for this molecule, we get carbon, fluorines, and our hydrogens here. Now, this is a trick. If you ever have a central atom and you have 4 peripheral atoms, so you know it's going to be a tetrahedral molecule, and you have 2 of each, like this, 2 and 2, okay, 2 hydrogens and 2 fluorines. If you're ever in that situation, when you draw the Lewis structure, make sure you put the similar atoms, peripheral atoms, next to each other or adjacent to each other, just like I did, instead of drawing it where they're across from each other. If you draw them across from each other, there's a good chance it's gonna seem like the dipoles cancel out. But if we looked at this in 3 dimensions, we would see that there is no across and up and down on these because we're in 3 dimensions. It wouldn't really matter how we drew it because the shape in 3 dimensions is a little different. So the trick is draw them together. And I've already done that, but let me just do that again here so we have more space. And we've got a molecule. Now let's go ahead and draw on our dipoles. We already said the carbon-fluorine bond is very polar, so it's going to be like this, right? And our carbon-hydrogen bond is very slightly polar towards the carbon, just slightly. So I draw tiny arrows pointing this way. So again, overall, if I look at this molecule as a whole, okay, where are the electrons getting shifted? They're getting shifted towards the fluorine side over here and away from the hydrogen side. So our molecule dipole is going to look like this for this molecule. That's going to give us a partial negative charge by the fluorine side and a partial positive charge by the hydrogen side. So this is a polar molecule. All right. Now, this is the same procedure you'd go through for determining the polarity of any molecule. The first thing you want to do is draw the Lewis structure, then draw the correct shape, keeping in mind that if you have a tetrahedral molecule and you have 2 of the same peripheral atoms, then you want to go ahead and draw those adjacent to each other. Also, then we want to draw in the bond dipoles, and based on the bond dipoles and the shape, we want to decide if the bond dipoles cancel out or if they don't and the electrons are shifted to one side or another. The last thing I want to mention is why are polar molecules, why do they have different properties than nonpolar molecules? So I want you to keep in mind that a nonpolar molecule is going to be kind of a blank slate. It's not going to have positive and negative charges. But a polar molecule that's called polar because it has a little bit of a positive side and a little bit of a negative side. And that has huge consequences on the properties between these two. If I take a nonpolar molecule, like methane or something, and I have a bunch of those methane molecules all together, there are really very little forces that are attracting those molecules together. There's not much holding them together. There are some very small forces. We call those van der Waals forces, that you'll learn about in other classes, but they're very minimal. And so there's really not much keeping these molecules together. That means for one of these nonpolar molecules to leave the rest of them does not take very much energy. That's why nonpolar molecules usually have a low boiling point. That means they become a gas with less energy, right? And an example of that would be carbon dioxide, a gas at room temperature. To make carbon dioxide into a solid, we have to get it very, very cold. Same thing with nitrogen or oxygen, okay, or hydrogen. Any of these nonpolar gases, they're gases at room temperature because they're nonpolar, they're light molecules, and they really have no attraction to each other. So it takes very, very little energy to get them to separate from each other and become the gas phase. With polar molecules, because the polar molecules have a positive and a negative partial charge, when they come together, those positive and negative charges are attracted to each other. So we, in essence, have a bunch of little magnets here, and because of that, these little magnets are going to want to stick together. And they're going to arrange themselves in such a way that the opposite sides are towards each other. And I'm not doing it great justice here, but we could see how they would arrange themselves. This would be like water, right? And a water molecule, by the way, water is relatively the same mass as these nonpolar molecules, which are gases at room temperature. But water is a liquid at room temperature. Why is that? When we put a bunch of water molecules together, they're attracted to each other. And you might remember they're attracted by hydrogen bonding, right? So there is a force that's keeping those water molecules, those polar molecules, together, kind of sticking them to each other through cohesion. So in order to get them to separate, to become a gas and leave the rest, we have to put a lot of energy in. Sort of like if we had a bunch of magnets stuck together, we'd have to put some energy in to pull them apart from each other. In a nonpolar substance, it would be like a bunch of marbles in a bag. It'd be much easier to just pull one marble away because they're not stuck together. So in nonpolar substances, they usually have a lower boiling point, which means they're often a gas at room temperature. And polar substances are going to be, which is like ammonia and water. These are polar substances, and they're often going to be found, they're going to have a higher boiling point. Okay, that means that in general, at room temperature, they're going to be found as maybe a liquid, or sometimes as a gas as well, but a liquid or even maybe a solid compared to their nonpolar counterparts. Let's see, why is it that polar stuff dissolves in water and nonpolar stuff doesn't? So if we look at a polar substance, we want to look at water. So if I have a beaker of water here, water has positive and negative charges on it, right? So we have all of these molecules, water molecules, that have positive and negative charges. Well, when they come in contact with another polar substance, maybe like sugar, and sugar or glucose is also a polar molecule, and it has positive and negative charges. When those compounds come in contact with each other, the negative end of the water molecules are going to be attracted to the positive end of the sugar. And the negative end of the sugar is going to be attracted to the positive end of the water. So what you're going to get is water molecules surrounding all of the polar sugar molecules. And that's what happens whenever a substance dissolves. The water molecules completely surround the other molecules. Now this only happens with polar substances, so polar water is able to dissolve other polar substances. And another way we can think about that is like dissolves like. That's because the polar nature of water, the partial positive and negative charges, are attracted to the positive and negative charges of the polar substance that's put into the water. If we take a nonpolar substance and we put it in water, okay, there are no partial charges on that nonpolar substance. So when we put a substance, let's say like vegetable oil, so I'll do a long chain of vegetable, oops, let's be red there. Long chain of vegetable oil, all right, and we put that in here. There are no partial charges. And in fact, because there are no partial charges, but there are partial charges on the water molecules here, that in essence makes them repelled from each other. So the water wants to be with itself. The water is going to stay with other, water molecules that have positive and negative charges. So they're going to kind of clump together. But then the oil is also going to want to clump together because it doesn't want to be around those charges. So we're going to get the oil layer separating from the water layer. That would be like a nonpolar substance, the oil. Okay, this is nonpolar, not dissolving in the polar substance. So, as we saw here, because the polarity of a molecule determines its properties, polar molecules that have partial charges dissolve in water, and they also have higher boiling points because they want to stick together. Whereas nonpolar substances don't have partial charges, they don't want to stick together, and so they have lower boiling points, and they also will not dissolve in water. I hope this gives you some insight on how we determine whether a molecule is polar or not, and also some of the properties and the reasoning behind the properties of polar versus nonpolar molecules. Thanks for listening. Have a great day, and Sko Ridge.